A light string is wrapped around a solid cylindrical spool with a radius of 3.5 centimeters and a mass of 50 grams. A 2-kilogram mass is then attached to the free end of the string, causing the string to unwind from the spool. What is the angular acceleration of the spool? So here's our spool, and we've got our mass here, and this mass is hanging. It's the one that's hanging. So that is the 2-kilogram mass that's attached. Okay. It says the spool has a radius of 3.5 centimeters or 0.035 meters. Okay. So the radius is 0.035 meters. And the mass of the spool is 50 grams or 0.050 kilograms. Okay? This mass was the mass of what was attached. So I'm just going to call it a bob. Who knows? Okay? And we want to know what is the angular acceleration. Angular acceleration, well, that is alpha. So we've got our picture, we've got our givens, we know what we're trying to find. How are we going to find this angular acceleration? Well, I know that this mass is creating a torque, which is causing this to accelerate, okay? Because we know a net torque causes an angular acceleration. And we simply find that torque is equal to the moment of inertia times the angular acceleration. So I'm going to try to use this because I know I can find a torque over here because I also know another equation for torque, and that is torque is equal to the force times the distance times the sine of theta. So I could find the torque, substitute it in here, and then look for alpha. I also need to know the moment of inertia, so we're going to have to figure that out as well. Let's start over here by finding the torque, okay? So the torque is equal to the force. Well, I don't have any forces over here in my givens, but I do have a mass. This mass is going to have a gravitational force acting on it, and that is the force that's going to cause the spool to spin. So that is the force we have over there. So we need to find the gravitational force. Well, gravitational force is equal to mass times the gravitational field constant. So the gravitational force is equal to 2 kilograms times 9.81 newtons per kilogram. And therefore our gravitational force is 19.62 newtons. I can substitute that in over here, so I have 19 and 62 hundredths newtons times the distance. Well, the distance is the distance from the point of rotation to where the force is being applied. So here's where the force is being applied. There's my point of rotation. So that distance is 3.5 centimeters or 0.035 meters times the sine of the angle. It's the angle when we start the point of rotation, travel to where the force is, go in the direction of the force. That is going to be, in this case, a 90-degree angle. Multiply all of that together, and I get a torque of 0.6867 Newton meters. And I can substitute that in over here. Well, what's left? In order to solve this, I also need to know the moment of inertia. Okay, I'm going to approximate this shape to be approximately a disk. And if we look up the moment of inertia for a disk, it is 1/2 the mass times the radius squared. So the moment of inertia is going to be 1/2 the mass of the disk. Okay, so that's the spool in this case. So it's 0.050 kilograms times the radius, which is 0.035 meters squared. So the moment of inertia is going to be 3.0625 times 10 to the -5th. And now I can substitute that in up here and solve for the angular acceleration. So I have 0.6867 is equal to 3.0625 times 10 to the -5th times the angular acceleration divide by 3.0625 times 10 to the negative fifth on both sides. Make sure you place it in parentheses. And we will get an angular acceleration of 22422.86 radians per second squared. So 22,422 and 86 hundredths.